Yes, welcome to this special summer edition of SBCL BCast, and we are very glad that Bronis de Supinski agreed to give a wonderful speech about heterogeneous system architectures, and with that, I'll give it to Nikolai to introduce him.
Okay, thank you, Torsten, and again, thank you, Bronis, for agreeing to speak. So, Bronis is the Chief Technology Officer for Livermore Computing at the Lawrence Livermore National Laboratory in the United States. He earned his PhD in computer science from the University of Virginia in 1998 and has been at Livermore ever since. Aside from his positions as professor of exascale computing at Queen's University of Belfast and adjunct associate professor at Texas A&M, throughout his career, Bronis has won a number of awards and other prestigious positions, including 2 consecutive Gordon Bell Prizes in 2005 and 2006 for, I believe it was materials and quantum simulations on the Blue Gene L supercomputer. He's won 2 R&D 100 awards, including for the stack trace analysis tool. And most recently, he is now an IEEE Fellow. And with that, Bronis, thank you, and take it away.
All right, thank you, Oli, for the nice introduction. So I'm going to talk about kind of the strategy that we have at Lawrence Livermore National Lab. So as it says, I'm the Chief Technology Officer for Livermore Computing, which is the supercomputing center at Livermore. I'm not the Chief Technology Officer for the whole lab. I'm not a physicist, so I'm not qualified for that position. Anyway, so to start with, sorry, it was my alter ego was slow in responding. So to start with, I just will briefly touch on where we are and talk a little bit about the systems we already have, because I can't really, like, a strategy is about where you're going in the long term, and you can't get to where you want to be if you don't know where you're starting from. So Livermore has been involved in computing since its founding, and we've cited a large number of significant systems. In the 22 years that I've been there, we've had the #1 system several times. We're currently the home of the #3 system on the top 500, which is Sierra, and we also have the #20 system, which is a very similar system to Sierra. And we actually build a large number of different systems. We cite a range of different systems for the Advanced Simulation and Computing program of the National Nuclear Security Administration. And so under that, we've cite large Linux clusters in addition to the advanced technology systems that are in the top 10 typically of the top 500. And so that includes systems that until the recent, at some point in their history were reasonably high up in the top 500. They're getting a little bit old in the tooth. We're in the process of finishing the contract that will allow us to field follow-up systems to these, but they're still significant systems. So in the near term, we'll be citing a system called El Capitan, which I'll tell you more about before the end of this talk. It will be one of the first US exascale systems. It'll be the first NNSA exascale system. We also do a lot of software development. These systems, these kind of Linux clusters, use our own system software stack based on Red Hat. It's called POS. I'm not going to tell you a lot more about that. You've probably, I hope you've heard of SPAC, which is kind of revolutionizing the packaging for large-scale systems, and we're developing a new, so Slurm, which you're probably familiar with, was originally developed at Livermore. That's a resource manager. We're actually developing a new resource manager called Flux that will be the resource manager on El Capitan, and also the upcoming CTS2 systems that will replace some of these systems. Anyway, so this is going to provide a glimpse into some aspects of our strategy to remain one of the leading centers. And as I'll tell you about, we expect system-level heterogeneity to be an essential aspect of that strategy. And what do I mean by system-level heterogeneity? Well, I'll get to that. But first, a little bit more about where we are. As I mentioned, we're part of the NSA. This sort of shows you NNSA includes Los Alamos and Sandia, as well as Livermore. And the NNSA field systems under two main lines, the advanced technology systems and the commodity technology systems. I kind of mentioned the CTS already. Sierra is actually the first ATS at Livermore, and that's really due to renaming. Previous systems at Livermore, like Sequoia and Blue Gene L, are really continuation, really previous systems in this line of systems. And El Capitan will be our next ATS. So first, a little bit about Sierra, which is the newest one we have. First, some eye candy. That's a picture of Sierra and a picture of one of the nodes. This is actually a Summit node, and you can tell if you look closely because, well, there's actually 3 GPUs, but you know, that's the way it is. So you're probably familiar with Sierra. I don't want to spend too much time on this, but it's a Power 9 Volta system. So each node has 2 Power 9s and 4 Voltas. The nodes are constructed so that the each Power 9 is connected over ND-Link to 2 of the keep happening. All right, to 2 of the Voltas. Then there's a fair amount of memory on each node, as well as some node local SSDs, and those are largely used for storing checkpoints. We also use them for having OS images so we can boot the nodes more quickly. All the nodes are connected by EDR over a fat tree. The total system has 4,320 nodes, which is a large fat tree, but well within the realm of what it can do. It's actually tapered at the top of the network 2 to 1. And that's because, frankly, our applications reflect a lot of work to minimize network use so that they can get the most out of the compute resources that we deploy. Anyhow, so as I said, you take 18 of these nodes, and that gets you a compute rack. And then you take 240 of those racks, and that gets you 4,320 nodes, which is a total of 125 petaflops in capability. And it's guaranteed not to exceed power numbers up in the 12 megawatt range. Actually, I think it ended up being a little bit lower than that, 11 to 12. Day to day, it's, you know, actual use is more in the like 8 megawatt range. Here's some more details on what Sierra is, but enough about where we are. So the basis of our strategy is that we think that the current system design principles are inadequate to handle future trends. And by future trends, this includes both the way we see our applications, so our workload evolving, but also trends we see in the hardware space, where there's getting to be a proliferation of different devices, and how would you accommodate that wide range of devices over the system. All right. So again, so back to where are we starting from? The question is, what do the systems have in common, right? And what we really see is that while many people would tell you Sierra is a heterogeneous system, I described the node, and then I said we repeated that 4,320 times, all right? And so to me, the system is rather homogeneous. Yes, the node itself is heterogeneous because we have two different types of processors on it, but once you figure out how to use the node, it's pretty much back to standard. We connect up a bunch of the same resource, and we try and use it well. We try and minimize usage of the network because we want to spend most of our money on the compute capability. So really, we pick out some node architecture. You know, we want it to be a star. We hope we love it. Probably in reality, it's really rather as generic as we can make it because we want it to be easy to use. And, you know, maybe we just lack enough creativity to think of doing something else. And then we say, well, we want to build a balanced system. The question that has to naturally follow that is, well, what do you mean by a balanced system? And we get a bunch of rules of thumb. You know, back when I was younger, we would hear, oh, well, you need 1 byte per flop. That isn't what we're able to achieve these days. And some would say, well, that's because we're not able to afford balanced systems. I think we get pretty good use out of the systems we build. So saying that the systems aren't balanced to me is not really entirely accurate. It's that we've figured out different ways to use it. And so what the workload is that maps to it, doesn't necessarily require those ratios that we have defined as balanced. In reality, that we actually design large portions of the system to be mostly idle once we deploy them. I mentioned that our applications work very hard not to use the network. So the network sits idle a lot of the time. Even more than the network sitting idle is we spend a fair amount of money on an I/O subsystem. So I didn't talk about the file system that we have on Sierra, but it's a pretty capable file system, all right? But since most applications, when they go to write data out to files, stop and wait for that to be done, and they know it's done so that they can then continue on, they're actually leaving the node mostly idle while they're writing to the file system. So they try to not use file I/O much at all, and so the file system sits idle most of the time. All right. So when we think about how these systems work, in some way we're not really using our budget that efficiently. Given the applications that we have to run, it's as efficient as we can run them. But if we could design the systems to allow things to be more asynchronous, we could actually use those components more efficiently, more consistently, right? Like the ideal system, in my brain at least, is one where all of the system is lit up all the time, completely and as much as possible, all right? So using everything at 100% utilization. Realistically, you would never get to that, but that should be our goal, is to be using everything that we spend money on as much as possible, right? Because if I could smooth out however I use that resource over time, I could buy a lot less of it if I'm not using it for large portions of the time. All right. So if you haven't gotten the drift yet, when I think about how to design a system, I'm thinking of it from an economic perspective, right? I have a certain budget that essentially the U.S. government passes down to me, and I get to spend this on a system. And my goal is not to get the highest possible place on the top 500 for that system. No, it's that we're going to run a real workload on it. We're a mission, or the Lawrence Livermore National Lab and NNSA are our mission organizations, and we have job to do, right? And so doing that job effectively is what we want the system to be able to contribute towards, right? And the best way to do that is if we use the money we are provided efficiently. So really, we want to think of system balance in terms of component utilization. So if the system really is well balanced, we're going to be using those components as well as the workload will allow us. All right. So as I've said, my intent is that we should be utilizing things at a high level and relatively constant over time. So that means we want to design the system in a different way that allows us to smooth out the workload and use everything more efficiently. But as I've also mentioned, we can only evaluate it in terms of the system workload. If the applications don't enable us to, if they don't require the network regularly, but they need it right now when they need it, then we're kind of at an impasse. What we can do maybe instead is defer use of the network by I/O and use that network resource for the I/O when the applications don't need it for communicating between processes running on the compute nodes. All right, so if you get the drift, you'll see that where I'm headed is that really we want to have the workloads evolve so that we can have high component utilization. That means we need more asynchrony. We need to not be sitting there saying, okay, I'm going to send a message to this other process, and I'm not going to go on until it comes back. I'm going to write this file, and I'm not going to do anything more until I know it's written all the way down to the disk on the parallel file system. No, I'm just going to say, here's the data. As soon as I know the data is successfully copied out of memory, go forward. All right. So doing that, we can then do things to evolve the system designs to exploit how our workloads are hopefully evolving. Other things that allow us to, ways that we want to evolve the workload are to reflect some trends we see in hardware. So you may have heard about a number of the new devices that are being developed. I'm going to tell you about some that we've deployed at Livermore that allow you to do AI very efficiently, right? And so we're exploring something we call cognitive simulation, which is building AI models into our simulations and basically short-circuiting some of the detailed physics computations. And instead of computing things, atomistically, we take an AI model that says, oh, well, this is a region of the simulation domain that we know well. We can compute the result of the physics that we would have gotten if we simulated them at that atomistic level and with that model and kind of jump ahead. All right. Well, that actually ends up requiring us to, again, build in more asynchrony into our systems, because we may be in a well-known domain, at part of the domain over here, but not over there. We may have, so most of our simulations use multiple kinds of physics. So maybe this part of the physics is in a well-known part of the domain. This other physics, we need to simulate at a more atomistic level. So we need to break apart all of these ties. That getting into the implications of that is a different talk than the one I'm going to give, than the one I'm giving. But that is a key aspect of how we get there, is breaking apart the applications to be more asynchronous. All right. But once we've done that, we actually find that we want to change the way we think about the system. Instead of designing so all the nodes are the same, it may be that these physics run better on a different kind of node. I may have an AI device that it's just not practical to put one on every node because not every simulation is going to make good use of it. And frankly, I might get the model to run faster if I group them together in a kind of separate AI volume in the system. All right. And so as we look towards our upcoming systems, we're starting to think about, you know, and working towards having this idea of system level heterogeneity be part of the system design. And the idea is that this will allow us to overcome some things like the slowing down, at least, of Moore's law that we see happening. All right. So first, I want to tell you something about the El Capitan system. So as I mentioned, that will be a system that we're building in partnership with HPE. At the time that we contracted for it, they were Cray, but they got acquired by HPE. They're all one big happy family. And we have chosen a AMD processor solution. So we'll have AMD GPUs and CPUs in the system. And that will be the main way the system will work. One thing I should stress is just because we have a heterogeneous system doesn't mean that we don't necessarily have a notion of compute nodes that may be repeated many times, even if not all of the nodes are identical. All right. And so many of the compute nodes will look like what you would expect. I mean, actually, in El Capitan, to be honest, it's a gradual step forward towards a heterogeneous system architecture. The overall system will be over 2 exaflops, so it'll be pretty significant. Now, the power we anticipate will be less than 40 megawatts, which was what the RFP requirement was. Frankly, we expect that it will be underneath the 20 megawatt per exaflop target that was that of kind of the initial targets of the exascale computing initiative in the U.S. I'll note that we are not power limited in our center. We are in the process of doing a pretty significant upgrade to our main computer rooms, the main facility at Lawrence Livermore, and that facility, it actually has 2 computer rooms that have a wall separating them, and it will have an 85 megawatt total capacity for power. The system will use the slingshot interconnect, and in relation to this talk, HPE is providing several critical innovations through non-recurring engineering activities. The system will end up using TOS as the system software stack, probably with some aspects of the Cray HPE Shasta software stack integrated into it. And then the thing I most want to tell you about is this innovative near local storage solution that it will include. And so that is something that HPE calls the Rabbit modules, and they will be a 4U device. And so the way that the system works is it will use HPE's Olympus racks. So the Olympus racks are rather large racks. They're not your standard racks that we build our Linux clusters in. They're very big. And in fact, they're big enough that we'll have a bunch of compute blades on one side that will house the main compute nodes. And then on the other side, the system is designed so you can have switch blades in there, so you can then use that to have your connections to your Dragonfly network. All right. So the way the system is designed, you can have a pretty significantly large number of switchblades. I guess some HPE customers may want a lot more network than we do because their workloads look differently than ours. I've already mentioned that our workloads avoid using the network for the most part, so we don't need any of it, anywhere near as many switchblades as the racks could house. Basically, it will be 1/4 populated in terms of the total number of switchblades, if I remember the numbers correctly. I may have that off by a factor of 2, but the key thing is that there's a bunch of, if we didn't do something else with it, there would be a bunch of empty racks or empty rack space sitting on our floor. So what we're doing instead is putting these Rabbit modules into that space. All right. And what a Rabbit module consists of is a switch module, which really is a PCIe network connected to a bunch of SSDs, so up to 18 SSDs, and a Rabbit processor board that has an AMD EPYC processor on it and connections to the Slingshot network. All right, but the real key is that the backside of the Rabbit S board has a bunch of PCIe connections that will allow us to connect to a bunch of the switchblades, to basically the switchblades in one compute chassis. All right, and so that means that we can access the SSDs in the Rabbit directly from the compute nodes, all right, as well as from the compute nodes out over the Slingshot network through the Rabbit P in that way. All right, here's a nice little picture of what our Rabbit will look like. HPE's done a really nice job of designing these. They spent a lot of work to figuring out how they could design it so that you can go and remove individual SSDs if they fail without having to take apart the entire device. And so that's why it's going to look like this. So while it's a board here that then has is designed in such a way that the actual SSDs are accessible from this angle here. All right. The software that it runs, well, it is a combination of software that HPE is developing and that we're developing. If you've heard of SCR, that's one of the main ways we figure our applications will actually use it. But the key is that we can actually run, access those SSDs in kind of 2 different ways, either as locally mounted storage, or we can run basically Rabbit Lustre servers on the Rabbit Ps that allow you to go and access it as shared transient Lustre file systems. All right, so we can run it as direct attached storage or as network attached storage. All right. It also will also have software solutions that will facilitate the automated movement of files from the Rabbit SSDs to what we call the capacity tier in our IO subsystem, or the permanent Lustre file system. So that looks like pretty much a traditional Lustre file system, parallel file system, and is where ultimately is the longer term storage for our applications. All right. A really important aspect of the Rabbits, though, is, I mean, we have a full-fledged processor there. We can run containers on those Rabbit Ps, and we can run anything we want in those containers. And we can then even connect RabbitP, connect containers running on RabbitPs over the Slingshot network using TCP/IP. All right, so we can really run anything we want on the RabbitPs, and we can essentially treat them as data analysis nodes. All right, and that's one of the things that we're very actively exploring, what we'll be able to run there and what use we'll get out of that. All right, so for our usages, the rabbits work really well. Most of our I/O workload is output rather than input. There is some input, and as we're moving more and more to using AI, there is more and more input, but still largely most of our I/O is O. All right, and we have really kind of two kinds of output. Output that is file per process, or output that is shared files. All right. For shared file per process, the idea is that we'll basically use locally mounted portions of the Rabbit SSDs and directly write over the PCIe network. So if you think about it, what we're really doing is building little nests of PCIe networks that we can access locally. And then if we need to move that file to the parallel file system, to the permanent Lustre file system, we can trickle it out. It's already on permanent storage in the Rabbits, so it's not critical. The applications don't need to wait for it. We're successfully smoothing out that bursty I/O traffic. But we can also do a bunch of other things. We can decide that a checkpoint file has been superseded by a subsequent checkpoint file, and so therefore we don't need to write it all the way to the parallel file system and never send it to the parallel file system. We can decide that, well, we're going to run, we've got our files on the Rabbits, we can run an analysis job on the Rabbits and do some data reduction before we store it all the way to the parallel file system. Now, I mentioned that there is another type of I/O of output, which is shared file I/O. The basic way that HPE expects to support that is they'll write out over the Slingshot network to the RabbitPs into these transient Lustre file systems. We're developing something that we call UnifyFS that will allow us to write two shared files, but over the PCIe network, which will then remove all of that bursty I/O traffic from the actual network and reduce interference from the I/O with other compute jobs, which we think will be important. In any event, as you can see, that basically what we're doing now is providing a mechanism through which we can do things. We have different kinds of nodes in these systems. We have these Rabbit kind of data analysis I/O nodes out there, and we can do data analysis or move off some of the I/O processing to them so that they don't interfere with the what we're buying the compute nodes for. All right, so I've already talked about that. So that's not the only way we can have system level heterogeneity. You may have heard that we've bought a Cerebrus CS1 that we've added to the Lassen system. I didn't update that, but I updated the other slide for that. It was number 17 on the November list. It's number 20 on the recent June list that was discussed at ISC last month. But that's integrated into Lassen. We have another system that's not actually on the top 500 because it's a little bit of a Franken system. Reflects kind of the more traditional way we've gotten system heterogeneity, which is that we bought the system over time. So we've got different kinds of GPUs in that system with different levels of capability, different GPU counts. It's primarily intended as a capacity machine where we run a large number of different types of jobs on it. So rarely would we have a job that spanned the whole system. It's actually about a 10 petaflop system, but we haven't run LINPACK on it. And that's called Corona. We've integrated a SambaNova 10 SN10-8R into that system. So these are two different types of AI accelerators that neither one of them would really have made sense to integrate into compute nodes, and I'll tell you a little bit of why that is. In particular, for the CS1, it's gotten a fair amount of press. It's the world's largest processor. I guess the CS2 has recently been announced, but the CS1, I saw a nice story on the CS2 in IEEE Spectrum this month, but the CS1 was 1.2 trillion transistors, 400,000 cores. It's a 20 kilowatt chip. It's the sort of thing that if we tried to put one in every compute node, we would not be able to have anywhere near 4,320 compute nodes. And frankly, most of our jobs would not make good use of, so they would sit there idle most of the time. So instead, we build a separate, if you will think of it this way, partition of the CS1 integrated into LLNL, right? And that's done right over the Mellanox InfiniBand network. All right. All right. So the SN10-8R is similar but different. It's composed of actually 8 AI accelerators, but they really can function as a single device. They are tightly integrated to be networked together and to allow machine learning models to be partitioned across those devices. We can also run on a single one. Both of these, both the SambaNova and the Cerebrus technology is interesting. Which one is better? Well, I guess that's personal preference largely. They're both pretty interesting to us, which is why we've gotten both of them. And in fact, when we look at their performance, they're pretty similar in performance at this point. When we look at them as a system, all right. Both of them actually are already integrated into these systems. This is the SambaNova system integrated into Corona. The integration is pretty similar. It's integrated over the OmniPath network that we've got in oh, wait a minute. No, I may have that wrong. That may have InfiniBand also. Actually, I think it is OmniPath. It's been a while since I looked at that. Anyway, so and this is the CS1 also integrated into LLNL. So these are actually deployed this way, and we are starting to run models over them. The idea is that basically we can run something like this Hermit model, which does some atomistic calculations. But instead of running the atomistic model, we run this Hermit model that allows us to replace this Cretan package. All right. And what we do is we end up for each node, for each zone in the actual overall simulation, shipping 42 singles over to the AI accelerators, running the model, and shipping it back. All right. And you can see we get fairly significantly higher performance. We can do the same thing with the SambaNova system. Looking at kind of some of the most recent performance on SambaNova here. This is very recent results, the first time that we've shown them. You can see this compares performance on the 10-8R to an A100. So this is basically using native PyTorch on the A100, and this is again native PyTorch on the 10-8R. This is using highly optimized CUDA graphs on the A100, and this is using C++, the C++ implementation of that Hermit model also. And so you can see that particularly at small batch sizes, we get significantly higher performance. Even at larger batch sizes, though, the performance difference between the A100 and the 108R is pretty significant. So we're seeing easily 5x on a transistor to transistor difference in performance. This shows you kind of the actual speedups achieved. And this is running just using one of the 8 Salmonova RDUs in the 108R. So it's actually using fewer transistors than we have available on the A100. Anyway, so that's kind of a high-level overview of where we're going. The El Capitan system will be a GPU accelerated system, so we're heavily bought into this path. We're getting great results on Sierra. I didn't detail them, but our application teams tell us that it's the first ATS system that they consider to have really delivered on the promise of being transformative, of really changing the way they work. They're now really able to do 3D uncertainty quantification studies on that system. We think that El Capitan will be similarly transformative for them. It'll take it from being something where they can do those studies at all to where it becomes routine to do those studies. I mentioned our CTS2 systems. We'll be announcing those probably end of the summer, maybe certainly by supercomputing. We expect that contract to be signed and announced. So that's basically what I have to say, is that the way we see systems evolving, there's going to be a wider range of devices and node types in them, and that applications are going to need to evolve to be able to use the fact that not every node is going to look the same.
Thank you, Bronis, for the excellent talk. Before we move to questions, I want to give a brief advertisement. Our regular SPCL vcast season will resume on the 12th of August in this same time slot, 6 p.m. Zurich time, with Professor Song Han of MIT, who will be discussing tiny machine learning.